Hello students, in the previous class we have studied about the nature of plane electromagnetic waves in different media. In that we have arrived two second order differential equations. In any media we find out the wave equation in terms of E and B. In the first class, that is plane electromagnetic wave in free space, we got del square E is equal to 1 by minus 1 by c square dou square E by dou t square, like this. So by solving those second order wave equations, we can able to find out the electric and magnetic field vectors, that is E and B are calculated from those second order differential equations. There is another way to derive these electric and magnetic field vectors E and B with the help of electromagnetic vector and scalar potentials. These equations, those equations which are in terms of magnetic vector and scalar potentials, can also be able to determine this electric field vector and magnetic field vector. Those equations will also satisfy the Maxwell's equations. So our aim is to calculate the electric and magnetic field vectors in terms of magnetic vector and scalar potentials, such that they should also satisfy the Maxwell's equations. So these potentials which are used to determine this E and B can derived from the basic Maxwell's equation. What are the four Maxwell's equations? Del dot D is equal to rho, del dot B is equal to 0, del cross E is equal to minus dou B by dou T, del cross H is equal to J plus dou D by dou T. Let us consider the second equation, that is divergence of B is equal to 0 or del dot B is equal to 0. We know that the divergence of curl of any vector is equal to 0. So if you compare these two equations, del dot means divergence. If you able to write down this magnetic field vector as the curl of any vector, such that the divergence of curl of any vector is equal to 0 must be satisfied. So I am assuming the magnetic field vector as B is equal to del cross A from the second equation in order to satisfy the divergence of curl of a vector. Here A is called magnetic vector potential. If B is equal to del cross A, it must satisfy the third equation. What is the third equation? Del cross E is equal to minus dou B by dou T, and B is minus dou by dou T of del cross A. Then this can be written as del cross E is equal to del cross minus dou A by dou T. So this is the del operator, which is the differential operator. These two operators are interchangeable. We can write down this equation like that. Then del cross E plus dou A by dou T is equal to 0, or curl of E plus dou A by dou T is equal to 0. This is also called, del cross is also called curl. So we have calculated the magnetic field vector in terms of one potential called vector potential as B is equal to del cross A. By substituting this value, we got del cross is equal to E plus dou A by dou T. One of the mathematical equation is the curl of gradient of any scalar is equal to 0. If you compare that, the curl of gradient of any scalar, that means this should be equivalent to some gradient of some scalar. Let us assume that this dou A by dou T is equal to minus gradient of phi, where phi is called the scalar potential. Then E is equal to minus gradient of phi minus dou A by dou T. So we have derived the electric field vector in terms of vector potential and scalar potential phi, and we have also find out the magnetic field vector in terms of magnetic vector potential. Let us remember these two equations. E is equal to minus gradient of phi minus dou A by dou T. These two equations will govern the calculation of electric and magnetic field vectors in terms of vector and scalar potentials. Let us substitute these two values in this equation. What is the fourth equation? Del cross H is equal to J plus dou D by dou T is the fourth Maxwell's equation. We know that B is equal to mu H, then H is equal to B by mu. Then del cross B is equal to by H. If you take it out, then mu J plus mu D is epsilon E, that is epsilon dou E by dou T. What is B? B is del cross A, that is del cross A is equal to mu J plus mu epsilon dou E by dou T. Del cross A is gradient of divergence of A minus del square A is equal to mu J plus mu epsilon dou by dou T of gradient of phi, that is dou by dou T of E is nothing but minus gradient of phi minus dou A by dou T minus del square A is equal to mu J. If you take this gradient of divergence of A to the right hand side, that is minus gradient of divergence of A. From this term, take minus gradient, minus mu epsilon gradient of the remaining term is dou phi by dou T minus mu epsilon dou A by dou T. Then take this minus del square A to the right hand side, or take all these terms to the right hand side and mu J onto the left hand side, that is minus mu J is equal to del square A this is dou by dou T, mu by epsilon naught dou by dou T. In E we have calculated minus gradient of phi minus dou A by dou T. So dou by dou T, another dou by dou T, that is dou square A by dou T square. This is minus mu epsilon gradient of phi dou phi by dou T minus mu epsilon dou square A by dou T square. Del square A. If you take minus gradient as common here, the remaining terms are divergence of A plus mu epsilon dou phi by dou T. Remaining term minus mu epsilon dou square A by dou T square. That is del square A minus mu epsilon dou square A by dou T square minus gradient of divergence of A plus mu epsilon dou phi by dou t is equal to minus mu j. This is one second order differential equation representing the electromagnetic potentials. How these four Maxwell's equations are converted into the second order differential equations in terms of magnetic vector and magnetic scalar potentials, right? So we have substituted these two values in fourth equation. From this fourth equation we have derived this function. Similarly, the two values, let us substitute these two values in the first equation. What is the first equation? Del dot d is equal to 0. D is equal to epsilon e. So then del dot E is equal to rho by epsilon. Del dot, what is E? Minus gradient of phi minus dou A by dou T is equal to rho by epsilon. Minus del dot gradient, that is del dot, that is minus del square phi minus divergence dou by dou t of divergence of A. Del dot is nothing but divergence. This divergence and dou by dou t are interchangeable. So minus dou by dou t and divergence of A is equal to this is del dot means divergence of gradient of phi minus divergence of gradient of phi minus dou by dou t of divergence of A is equal to rho by epsilon naught. Take this minus to the right hand side term, that is divergence of gradient of phi plus dou by dou t of divergence of A is equal to minus rho by epsilon. Let us add and subtract the term like this, that is, let us add and subtract mu epsilon dou square phi by dou t square. On adding and subtracting mu epsilon dou square phi by dou t square, this term is del square phi minus mu epsilon dou square phi by dou t square plus mu epsilon dou square phi by dou t square, remaining term plus dou by dou t of divergence of A is equal to minus rho by epsilon, that is del square phi minus mu epsilon dou square phi by dou t square. If you take dou by dou t as common, the remaining term here is divergence of A plus mu epsilon dou phi by dou t is equal to minus of rho by epsilon. These two equations are the second order differential equation in terms of A and phi. These two equations are also called as Maxwell's equations in terms of A and phi. These two are called electromagnetic inhomogeneous wave equations in place of 4 Maxwell's equation. We can substitute in place of 4 Maxwell's equation, we can replace these equations also. 4 equations and these 2 equations are equal, one and equal. In both these terms, we have a constant term, that is divergence of A plus mu epsilon dou phi by dou t. If we have chosen A and phi such that divergence of A plus mu epsilon dou phi by dou t is equal to 0 for a set of values and A and phi. If this quantity becomes 0, this condition is called Lorentz condition. Then these above two equations will become del square phi minus mu epsilon dou square phi by dou t square is equal to minus rho by epsilon, or del square A minus mu epsilon dou square A by dou t square is equal to minus mu j. Then these two equations will be converted into these two equations if they satisfy the Lorentz condition. From these two equations also we can able to find out what are the electric and magnetic field vectors, and from these equations we can calculate the magnetic vector and scalar potentials. This is regarding the electromagnetic vector and scalar potentials. This condition is called Lorentz condition. These two equations are the Maxwell's equations in terms of A and phi.